Good evening. So today we shall look at tutorials. We are going to solve questions on strain gauges, strain gauge rosettes, and then we're also going to look at circuits, questions on circuits for converting change in resistance to change in strain. So we are going to go straight ahead and start, but before then, let's look at a little bit on strain gauge. What is a strain gauge? Strain gauge is a small piece of electrical wire. It can be made up of a foil or a small electrical resistor made up of probably copper. So the strain gauge is used to measure what? Strain, but we can't measure strain directly. It uses the principle that what? Electrical resistance is proportional to what? Strain, whereby we have what we call a constant. So what happens actually is that this resistance wire, when loaded, reacts to what? Change in resistance. And so this change in resistance is now used to be able to measure what? The strain, which is on the right hand side, using the our intermediary, which is the constant SA, which every strain gauge material has its own what? Constant. So in essence, the strain gauge, we can liken it to a kind of sensor or a transducer, since it doesn't measure strain directly. That is used in measurement of, for example, other quantities: force, vibration, acceleration, and many other quantities. And also some of its application is in rail monitoring, rail line monitoring for trains, in the monitoring of dams, in inner lining of dams, and so many other applications. Before then, let's start with the other exercises. I have other exercises in PDF also. So this is from the textbook, Experimental Stress Analysis. So the first question here is, okay, before the question, anyway, we are going to derive some of these equations. The first question here is, develop the single value equation for the counterclockwise angle between gauge A of the 3-element rectangular rosette. So in this case, here is asking us to derive the complex stresses for a 3-element rectangular strain gauge rosette. Then the next one also is for a delta. 8.19 is for a delta rosette, and then 8.15 is some questions. So let's just go briefly through it. So in essence, I've made the summary of some of these derivations here. These are some of the common configurations we can have of the strain gauge. This is uniaxial. Here we have biaxial. Here is 2 elements, while here is shear. This measures shear. This will measure what? In the 2 axes, right? Here it can measure the vertical axis, which is the y-axis, and then the horizontal axis. And then here we have 3-element rosette. This is used for comprehensive stress analysis, for holistic stress analysis, whereby we can be able to determine our principal stresses. This is called 3-element rectangular. This is delta, and this is stacked. Can you see why it is stacked? I hope you guys are with me, please. Hello, class.
Yes, sir.
So let's start with each of these strain gauge. But before then, we already know that the strain gauge doesn't measure strain directly, so it uses the principle that change in resistance over initial resistance is proportional to what? To strain, where we have a constant called the sensitivity, which is SA. So let's derive these equations for each. So for number 1 here, this is uniaxial. This is basically, we can say, is the same thing as what? If, for example, the strain gauge material, the gauge material here is to measure in just one axis, you can say it is measuring in what? In the y-axis. Here it can measure in x and y axis, right? Here is measuring shear. So let's look at 3. 1 and 2 automatically is known, right? Because here we can say it's the same thing as E what? EX, and here is the same thing as what? E, the strain in the y what? Direction. Here it can be E what? Strain in the y direction. But for this one, let's derive it, because number 3 here measures the shear, right? and we call it what? Is it here? We call it 2 element 90 degrees planar shear what? Rosette. You can see there are 2 strain gauges. That's 2 elements. So let's, but before then, we need to understand what is complex stresses. So 4, 5, and 6 can be used to measure what? To generate or resolve complex strains. Here, what it means here is for complete stress what? Analysis. So in example here is 2D. We can have 2D or 3D. 3D here is EXX, EYY, and EZZ. It means with this element, we can with this with 4, 5, and 6, you can be able to make what? A complete stress analysis. Here is EXY, and here is EX what? Z. Here is EYX, and here is EYZ. Here is EZX, EZY. If the material is isotropic, it means the material has uniform property all through. EXY is equal to EYX, and you can also represent it with this symbol, right? So for the 3D, in this case, we are going to have 6 variables. In this case, we will have EXX, the normal strains, sorry, EYY, and EZZ. And then you can have also the other 3 shear strains, which is EXY, EXZ, and EYZ. So for 3D, you will end up from 9 to 6 if the material is isotropic, while for 2D, you'll end up from 4 to 3 if the material is isotropic. So here we said we can be able to do complete stress analysis. It means here we can be able to determine the maximum. So the maximum, the principal stresses, at the maximum principal stresses, the shear stresses are what? 0 for 2D. And then we can be able to use the maximum principal strains to be able to determine our corresponding maximum principal what? Stresses, so that we can be able to determine factor of safety, whether is going to be safe or the loading applied is beyond the safe limit. So this is what we mean by complete stress analysis. So 4, 5, and 6, we can be able to use it to carry out complete stress analysis of components. So let's determine these complex stresses. For example, let's begin with 3 also. So for 3 here, it we said is a 2-element shear rosette. So you can see the configuration 45 degrees. So even here is going to be 45. Here also what? 45. So we know that the state of strain at any point is given by this equation, E theta up plus some of the component of the complex stresses, right? This particular equation. So let's derive the complex stresses for a shear element, 2-element shear rosette. So here EA is at the first angle. A is at what? We have to have our reference. Our reference is at the 0 line here, 0 degrees line, and so A is tilted 45 degrees from the axis, right? Are we following, class?
Yes, sir.
So A is tilted 45 degrees, not like that. So using this general strain equation, so EA, so now the strain at A is at angle 45. So when we impute it, here cos 2 theta is going to be cos 90, and then here the shear strain and then sin 90. Remember, cos 90 is what? Is 0. So we'll end up having this equation 1. And then the second strain gauge, which is B, EB is at what? When you add it up from the reference 0 here, is going to be at what? 135. And so here, cos 2 theta here in this case is going to be 270, and sin 2 theta 270. So we'll end up with this equation. So we can solve these 2 equations to determine our shear strain. In this case, when you subtract B from A, you will end up with what? The shear strain. And the shear strain is the difference between the 2 strain gauges, EA minus EB. In this case, we cannot measure normal stresses, so this only measures what? The shear strain. Then the next one is this is called two-element planar shear rosette. Two-element planar shear rosette. Then let's look at rectangular rosette. That's three-element rectangular rosette. Right. So similarly, also we use the same way using the general strain at a point. So for EA, if you look at this, the rectangular rosette, the first strain gauge is at what? 0. Is aligned at the 0 axis here. Our origin 0 axis, so it means E theta is equal to 0. So the strain here, we have cos 0 is equal to 1, and so sine 0 is 0. So in this case, EA exactly is equal to EX, which is one of the complex stress, EX, for a plane stress analysis. Then the next one is at what? The second strain gauge is tilted at what? Is at an angle 45 degrees. So when we enter this, we have it as equation number 2. And then the third strain gauge is at what? EC is at 90 degrees. And you know, cos 2 theta, which is cos 180, is minus 1. And sine 180 is 0. And so we'll end up with EC is equal to EY. So EA in this case is equal to EX. And EY is equal to EC. So what we don't know is the shear strain. So substituting equation 3 and 1 in 2, we can be able to determine the shear strain. So in this case, and these are the values, right? So the next one is the delta. Similarly, using the general strain at a point, we can be able to determine for each of the strain gauge. You can see this one is a little bit spread out. So this type of strain gauge is the same thing as this, gives the same result, and also gives the same result as this stacked, right? So the second and third, they are all spaced completely at 120, but they are the same. The same result is gotten from the analysis. So let's start with this one here, the left-hand side, which we call this three-element delta rosette. So for 4 and 5, we can be able to determine the normal strains and the shear strain. So here, EA is at the origin here. Let's assume it's aligns 0 with 0 angle from a 360, angle. So when you substitute it here, we are going to have cos 0 is equal to 1. So we'll end up with EA is equal to EX. When theta is equal to 120, it means cos 2 theta will be 240, and cos 2 theta is minus half, and cos 240 is minus half, and sine 240 is 3 by 2. So we'll end up with this equation 2, and then we also substitute for EC, and also we'll end up with equation 3. So in this case, we can add equation 2 and 3. So when you add equation 2 and 3, we can be able to determine one of the normal strains. And then also when we add equation 2 and 3, we can be able to determine one of the complex strain, which is EY. And also when you subtract equation 2 from 3, we can also be able to determine the shear strain. So in this case, the 3 complex strains for 2D are EX, EY, and the shear strain. Remember, whenever you see EX, is the same thing as what? EXX. EY is the same thing as what? EYY. They are the normal strains, and then we have the shear strain. The shear strain, we can decide to EXY is equal to what? Or we can use is the same thing as this symbol, right? EXY. So also provides the normal and the shear strain. So let's go directly to our problems. So let's look at the first question here. The state of strain at a point A on the bracket is measured using the strain delta rosette as shown in the figure. So this is delta rosette. This is the diagram here. You can see the way it is. It is this particular version. This is the version of the what? Of the delta rosette. And so we are given this EA is equal to minus 150, and EB is equal to 150 micro, and then EC is equal to 300 micron. You know, that's micron is 10 to the power of minus what? Minus 6. You see, the strain is very, very what? Small. And that's why we can't even difficult to measure strain directly. And that's why we are using strain gauge, because strain gauge is like a transducer, whereby we can be able to measure, can be able to detect the change in resistance, which is very sensitive. You know, there is high sensitivity in determining change in resistance than directly determining strain. So from the change in resistance, we can then use the formula to be able to determine the what? The strain. So we are also given the material property, the Young modulus, the Poisson ratio, and here we are also given the yield stress. So what we are asked to find is the principal strains. If the question now asks you to prove, for example, it says develop the single valued equation for the counterclockwise angle between gauge A of the 3-element rectangular rosette. It means you have to prove these ones, right? Whether it is 3-element or whether it is delta or rectangular. But in this case, we are not asked to prove. It just says determine the principal what? Strains, right? So in this case, we just go ahead and determine the principal strains. So given this, the equation for the principal strain is given EX plus EY. This is the equation. And so we can substitute and determine our principal strain. So when you do it correctly, in this case, first you have to determine the complex stresses from the delta rosette. It means, though we are not asked to prove, so you can just go ahead. If you know the formulas offered, if you don't know, you can prove them, right? So EA here, remember, is the same thing, minus 150. EY is a formula, so we'll have to impute and get the value. In this case, we are going to have 350, and the shear strain is given by 173.2 divided by 2, because the shear strain is divided by 2, and this is equal to 86.61. So, and then you can impute it directly, and then you can be able to determine which is 364.58, and then the other is going to be 164, the other principal strain. So at the principal strains, the shear stresses are 0. So the next question, we are asked to determine the maximum in-plane shear strain. And so in this case, we are going to look at a Mohr circle and then the maximum absolute, right? So since we know this, we can rearrange these principal strains. From the two principal strains, we know that the first one is the maximum, which is 364.58 micron. Remember, there is micron on both. Remember, one of the principal strain is going to be what? 0. And so since we have negative, the negative is going to be the what? The minimum. So in this case, 164.58 is going to be our minimum. And then we'll also have what? 0. So in this case, remember, these two values is our in-plane. That's the plane we are dealing with directly, that we're able to determine these two principal strains. So let's determine. So we'll have several planes, 3 planes in essence, but let's see how we can determine them and then compare our answers with the Mohr circles of strain. So E1 minus E2, when you do that, you are going to have 182, the shear strain, 182.29, and then this we are going to have 264.58 micron. So we can also compare these results. So these are the two maximum shear stresses, right? So in essence, this is the in-plane, which is the maximum, right? So the in plane is the maximum absolute. Maximum absolute. The absolute is the maximum, right? So, but we can compare this on a Mohr circle. So, to draw a Mohr circle, you need 2 points, P1 and P2. You draw your axes. One of the axes is going to be EX, EY, your complex normal strings, and then the y-axis is going to be your complex shear strain. So let's get these 2 points. Remember our EX, we have gotten it earlier. These are the values we are going to EX, EY, and the shear strain. So first EX is minus 150, and then the shear strain, remember, is 173.2, but we have to divide by 2 because the axis is divided by 2, so it's going to be 173.21 divided by 2, which is equal to 86.605. And then the second point is going to be EY, the negative of the shear strain. So the first point is the one of the normal strain with the shear strain, the other one is the other normal strain, and then the negative. So the second one here is 350, and then minus 86.605. So here we can come here and sketch it. 150. So here is our P1, and here is our P2, right? So you draw what? A horizontal line to touch the 2 points as the diameter. Don't mind my line is not straight. So with this diameter, you can draw what? A circle. So just draw a circle. Draw a complete circle. Don't mind my drawing. So this is the complete circle. So with this circle, you can be, so in this case, this is our maximum. This is our E1, which corresponds with, let's see what, well, in this case, you are expected to use your mathematical sets. What are we having as our E1 is 364. Here it also is before, you can see the result is close to 400. So this is our E1. And then let's look at our E2. We can see that our E2 is what? Our second principal strain is negative. Is minus 164. And so we can see here, we can liken it to minus 164. Here is close to minus 200. So we're able to see that the second principal strain is negative, right? Which is the minimum. And this is E what? 3. And then we'll have the intermediate, which we designated 0 to be E2. And so we go ahead and draw the other circles, since we have 3 principal strains. So we draw a circle of E1 and E2. E2 is the intermediate. And also we draw a circle of what? E2 and E3. But then we know that the maximum in plane is our maximum absolute, which is this one here, right? Which is this maximum is going to be approximately 264. So if you look at it, here is 100, here is 100, here is 200, and approximately, since my circles are not accurate, and then the second one, we can have the second, maximum shear stress to be at this point, which is less than 200. And what are we having here? 182.29 micron. So this is it. You can see, you can also be able to determine using the Mohr circle. So the next question is to determine the orientation angle from gauge A, or from A gauge. And this is the formula used to determine that, right? So the orientation angle is tan 2 theta, and so we should be able to tan 2 theta equal to the shear strain divided by the differences in the normal strains. And this particular angle is given as theta is equal to minus 9.55 degrees. So this is what it means. Here, this is our delta strain gauge rosette, but the actual orientation is at what? Let's say this is our minus 9. Minus is going opposite, right? Clockwise is going clockwise from 360. So in this case, this is our minus 9.55. And so also the second strain gauge will also tilt. So in this case, if you want to determine the angle oriented by the second gauge, you will have to add what? This theta 1 for gauge what? For gauge A. For gauge B is going to be minus 9.55 plus 120. But remember, if it is rectangular strain gauge, then you will add what? 90. But in this case, it's delta, so you will add 120. So you can also see that this angle corresponds to also this, because this is the angle you need to tilt the initial complex strain to be able to arrive at the maximum principal strains. So this is the same angle, which is what? 9 points. You see, you can also see from here it is negative, minus 9.55 degrees. So this is the orientation angle. It means the angle you need to orient your complex strains to arrive at the what? At the principal strains. So next is you determine the corresponding principal stresses are given as this. If you enter the formula correctly, we'll have it as the first one is going to be 69.15 megapascal, and this is going to be minus 13.21 megapascal. So these are the stress, maximum normal stresses. These are the corresponding normal stresses from the normal strains. Remember, at the maximum normal stresses, the shear stresses are 0. So we can arrange them here in 69.15 megapascal. Remember, since we have negative, then our intermediate is going to be 0. So we have negative here. So these are our maximum shear stresses. These are the maximum shear stresses. But since we are looking at complete stress analysis, it means we also have an intermediate. The last one is going to be what? 0. Since we are looking at a planar scenario, right? Plane stress. Thus, maximum shear stress according to Tresca. So we're asked to determine the maximum shear stress. Here we're asked to determine the maximum shear stress according to Tresca and von Mises. So Tresca is maximum shear stress theory, and the von Mises is the shear strain energy theory. So let's look at the two and see which is more conservative. So for the Tresca maximum shear stress, all we need is the maximum minus what? The minimum. And so the negative is the minimum. And so when you do it correctly, you will end up with 41.18. So then the factor of safety, and for the maximum shear stress, it says the yield divided by 2. So the yield divided by 2 is what? 120. So we have 60 megapascal. Remember, so if this maximum shear stress from the complex stress is less than that of the yield divided by 2, then it means the loading is safe. And in this case, we can go ahead and determine our factor of safety, which is right hand side, which is 60 all over, or which is yield divided by sigma 1 minus sigma 3, which is 60 divided by 41.18. And in this case, it will give us 1.46. We can also use which is the shear strain energy theory. We can also use the shear strain energy theory, and this is the theory it says. And so when you compute it directly, we expect that it should be less or equal to the yield squared all over 6 multiplied by the shear modulus. So this value here is giving us, in this case, if you look at it, we can 6 can cancel here, which is going to be equal to what? 2. So this left hand side, it will give us a value of 5869.5. And so if this value, so you can do it's less than actually, which is here is going to be 120 squared divided by 120. The G also cancels, so it's just 120 squared, and I'm sure 120 squared is greater than 5869.5. So in this case, we can go ahead to determine our factor of safety, and our factor of safety is going to be what is on the right hand side over what is on the left hand side. So 120 squared all over 5869.5. So because the shear strain energy theory, the terms are squared, so in this case you have to also square. You can see it's also 120 is squared, the yield, so you will have to square so that you can be able to get your correct factor of safety, and it's going to be equal to 1.57. So in essence, this is our factor of safety using shear strain energy theory. So look at it, which one is more conservative? I think the conservative means it means you are going to economize material. So it means the maximum shear stress energy theory is more conservative. The first one is more conservative. That's the stress car is more economical, right? That's conservative, economical. Factor of safety tells you how you can be able to either economize or make your material waste, right? Because you are not using material to its full potential. So you can see the value for the shear strain energy theory is greater.